Okay. At this point, we will try to discuss other properties of your Laplace transform, which are really usable in solving practical problems or real problems encountered in engineering practice. Okay. So, but before we proceed, we basically first discuss two auxiliary functions that are used widely in engineering applications in order for us to describe a more realistic forms of your signals. Okay? Basically kasi what we have in some engineering in some engineering problems is that we have a system, okay? And that system takes in some kind of an input and then it produces an output. Okay? So, what we would like to find out is how would this system react to a given input? At least in theory, okay? Because we might have an idea of the model, okay? Of the model of your system. And this model maybe since our system may be considered as what we call dynamic system. Okay, this model may actually be differential equations. Okay, may be expressed in terms of differential equations. Okay, but um, how we analyze this system now in terms of how they actually would behave if if it accepts certain inputs. Okay, but so far what we can only process, okay, or what we can only analyze, uh, what we can only offer our systems as input signals, at least in theory, okay, is signals that are known functions, okay, like for example sinusoids or exponentials or constant signals, okay, that are convenient for us to mathematically describe and write, okay. But in a more realistic in a more realistic sense, that we still have we still have those set of inputs that are not really or cannot be really described by certain simple mathematical formulation. Okay. Say for example, if you have been if you were able to encounter this in your electronics course, the half wave or the full wave rectifier signal. Okay. Um, this this half wave or full wave rectified signal. Okay. Say let's take the case first of the half wave. Okay. So this half wave rectified signal basically is a sinusoid. Okay, that is cut off of its negative value. Okay, so as you can see that these are sinusoidal pulses that that periodically come out, okay, for a certain duration. Okay, so these are your half wave rectified signal. Now, um, of course, it is obvious that this cannot be described by, say, for example, a sine omega t formulation, because essentially this is not a complete sine wave. This is a sine wave that you have to clip the negative part of. Okay, so signals or functions that are this, okay, which serves as input signals to our to systems that we would like to analyze, okay, are very common in engineering practice. Okay, when we have systems, we would there would be a need for us to analyze these systems with this kind of signal. How would they behave if this kind of signals um, presented unto them as inputs? Okay, so before we go to the the Laplace transform. Okay, before we continue with the Laplace transform, let us define here in this section we will define the unit step function. Okay, or what is basically called also as the Heaviside function. Okay, it is u of t minus a. Okay, and on the next section we will describe the Dirac delta function. Okay, this one we will describe this on the next section. Okay, so so we deal first with unit step function. So the unit step function or the Heaviside function. By the way, Heaviside is an engineer, okay, who actually first proposed to use Laplace transform in order for him to solve some of the pressing problems in electrical engineering. Okay, so he was one of the first to do that. Okay, so the Heaviside function is denoted as u of t minus a. Okay, now let me remind you that u here is the name of a function. U is not simply a variable. Okay, it is a function name. Okay, much like in f of t. Okay, much like in f of t, f here is a function name, and t is a variable, or in particular, that's an independent variable. So same thing with this one. So u is a function name. So this is the function name that we will assign to the unit step function. Okay. Now you have here the independent variable. Okay, t minus a. Okay. So we are writing your Heaviside function in terms of its functional notation. So that is the name, okay, as a function of the independent variable. Okay, but here the independent variable is essentially t. Okay, but in this case, when you subtract something, or when you subtract a number to the independent variable, the tendency is for your function to be shifted, okay, in time. So okay, in a general form, if here, okay, if a here is a positive number, so meaning you're subtracting from t, okay, your function shifts to the right. While if a is negative, essentially making this u of t plus a, okay, essentially making this u of t plus a, okay, your function shifts to the left. Okay, so we will be dealing with this one a little bit more, because this is a more practical, this is more realistic and more practical in terms of practice, because this involves delaying, okay, or introducing a delay on your function or signal. Okay, so at this point I might be interchanging the term signal and function, okay, more often. So please be reminded that I actually refer to them as the same. Okay, since I'm actually trying to engage you now in some application, okay, of this mathematical tools. Okay, so having this as a kind of having this or introducing a delay on your function is much more realistic in it's much more practical in practice than advancing, because basically advancing means you are taking the future, okay, taking the future value of the signal now, which is not possible. Okay, it's like pulling what happens what would happen in the future today, or watching what would happen in the future today. So that is not possible. But delay is a more realistic concept. Okay, so we basically delay our signal. Okay, okay, but in its most basic sense, it's if a is actually 0, that is your signal doesn't have any amount of delay in it, your unit step function would actually look like this. Okay, so your unit step function ninyo is defined as 1 when t, this is simply u of t, when t is greater than or equal to 0, okay, and 0 when t is less than 0. Okay, although in some like in this in the reference that I'm using, the unit step function is using pala not equal to. Okay, so it's just simply greater than. Okay, yun pala yung definition niya. Okay, so here what happens is that at time 0, your signal switches from 0 to 1. Okay, or your signal changes its value from 0 to 1. Okay, so here's what it implies, okay, in practice. Let's say you have a system. Okay, let's say you have a system and you would want to measure the response or the output of the system. When I again here I would be interchangeably using I would be interchangeably using um, output and response very often. Okay, because they are actually equivalent terms. Okay, now um, say for example you are trying to measure the response or the output of the system or its behavior. Okay, when it accepts a certain input signal. Okay, that um, this y-axis, okay, this y-axis itself, where t is equal to 0, is the boundary of um, when you are not measuring anything, okay, and when you are to measure the behavior, okay. And at t equals 0, this t equals 0 is the moment that you decide to measure, okay. It's the moment that when you say, for example, switch on switch on the signal, okay? Switch on the signal to the system, okay? Or basically that's when you decide to measure things up, okay? So that's the significance of time equals 0 here. Okay. So as you can see in this manner, that if you actually switch if you actually also decide to switch the system on at time equals 0, okay? And then apply a constant input into that. Okay, a constant unit input. Unit means the magnitude of the input is 1. Okay, that's why it's called a unit step. It means that you are now trying to analyze the behavior of your system at this point. So that half, okay, that half when your t is positive, okay, is that um is that region of or is that period of time where you are trying to measure or where you are analyzing the behavior of your system. But as long as you are not deciding on anything, right, here, as long as you are not deciding on measuring or analyzing the behavior of your system, then you are here. That is when t is less than 0. So I would like you to understand it that way. Okay. Now, the delayed unit step function, okay, u of t minus a, is a delayed version of the unit step function here, okay, for a units of time. Okay. So, this is important because we might want to if you remember that earlier I was telling that this t equals 0 might be the moment that you switch the signal on to the system. It might not be the case in some um, in some situations. Okay. You might want to decide now, okay, at t equals 0 to measure the behavior, but you might want to switch the input signal on later. Okay. So, pwedeng ang nangyari is that here is when you decide that I would want to measure the behavior of your system. Okay. I want to measure the behavior of your system. But here is the point where I would like to switch on the input to my system. Okay. So, you're trying to also see how your system behaves without the signal. Okay. And how it behaves with an input signal. So, this amount of delay that you put in deciding to switch on the input to the signal, okay, is the parameter A, okay, and it's the delay, okay, that you have introduced. So in this case, again, this is the magnitude of this is 1. The magnitude of this is 1, excuse me. But this time, this unit step signal now is defined as u of t minus a, okay, and the value of this is 1, okay, when t, okay, is greater than a, and 0 when t is less than a. Okay, so that's the difference between those two signals. Okay, now, next is how would we like to okay, let's talk about firstly, let's talk about the its Laplace transform. Okay, so here is the Laplace transform of the delayed unit step signal. Okay, and take note that if a is equal to 0, okay, so here, the Laplace of u of t minus a is equal to negative e raised to negative as over s. Okay, and it assumes that your s is positive. Okay, now here, if you actually set a equals 0, so that means we're just simply getting the Laplace transform of u of t. Okay. This simply reduces to since a is 0, e raised to negative as becomes 1. Okay. And and in that case, e raised to 0 is 1 over s. Okay. And as you can see, this Laplace transform is actually from table 6.1. This is actually the Laplace transform also of the constant 1. Okay. Which, again, if you actually interpret this signal, okay, interpret this function, the constant function 1 and this one, they are actually the same. Which is basically the same when we are considering the limits for your Laplace transformation integral, okay, Laplace transform integral, in which the limit is 0. So essentially, the integral ignores whatever is to the left of t equals 0. Okay, so ito kasi, this is its graph. Okay, this function is this. Okay, but when you say that f of t, okay, is equal to 1, okay, essentially, that is 1 for all t. Okay, that's a constant 1 for all t. Okay, ito, let me show it to you through Desmos. So here's the difference. When you have f of t equals 1, okay, when you have f of t equals 1, essentially, you have your 1 constant all throughout the time interval. Okay, that is from negative infinity up to positive infinity. Your f of t is 1. Okay, that's f of t equals 1. Okay, but when you have u of t, okay, the unit step function as we have described here, okay, as we have described here in this part, okay, you have some kind of this. So as you can see, the signal switches, okay, at time equals 0, okay, your signal switches from a 0 value to a unity value. Okay, and that is why a practical use of the unit step signal is in switching. Okay, when you have signals that switches, okay, or when you want to switch on and off your signal, okay, so that it becomes or it becomes another shape or form. Okay, then you can use a unit step signal to describe such kind of input signals. Okay, and so again, the difference between f of t equals 1 and u of t is glaring. Okay, again, f of t is defined for all t, while u of t is just defined for is non-zero for positive t, but is 0 for negative t. Okay, but in our in terms of Laplace transform, in terms of our definition to Laplace transform, essentially f of t equals 1 and u of t becomes 1 and the same. Okay, mainly because of how we define the integral of the Laplace transform. Okay, or how do we define the Laplace transform integral, which has a lower limit, okay, which is an improper integral, okay, that covers the range 0 up to infinity. It covers the range 0 up to infinity. So my point is, whatever is to the left of 0, of t equals 0, okay, whatever is to the left of t equals 0, meaning here, whatever is to the left of, this is t0, this this black line here, okay, is t equals 0. So whatever is to the left of that line, okay, is actually ignored by your Laplace transform. Okay, it actually isn't ignored by Laplace transform integral. So the Laplace transform integral, as we have defined it, only concerns itself with when t is positive. So that is why when we only consider the right side of this time graph, okay, then we can see that these two are the same. Okay, and therefore they would arrive at the same Laplace transform. Okay, so that should explain the equivalence between u of t and 1 as a constant function. But going back here, we have u of t equals I mean this one, the Laplace of this is u of t equals a. Okay, so e raised to negative as over s. Okay, so the unit step function is a typical engineering function made to measure for engineering applications, which often involves function, either in terms of mechanical systems or electrical systems, that are either off or on. Okay, you can actually choose to say for example you have a continuous you have a continuous source of signal that is supplying input to a certain system. And then you would want to experiment what would happen if you actually turn the signal on and off. Okay? So you might be experiencing, or you might be wondering how you could actually represent those that kind of signal into a compact mathematical form. Okay? So that you can actually use tools of mathematics in order to analyze these kinds of behavior, okay, for a system, given that the input is not really a standard mathematical function. Okay, so how do this unit step play a role, or how do we actually express this into mathematical form? Okay, or how do we use them in analytic analysis, in analytic method of analyzing your system. Okay, we start with how do we interpret how we interpret the unit step function, especially when it gets multiplied with a certain standard function. Okay, say here you have a function that is defined as 5 sine of t. Okay, this is 5 sine of t. Now, again, this is a standard function. This is a standard sinusoidal function. Okay, where 5 is its amplitude. Okay, and its frequency, or its it's the multiplier, or the scale of t here actually has something to do with the periodicity of your signal. Okay, so we define this this constant, or this parameter that is multiplied to the time variable, okay, or that scales the time variable of your sinusoidal as 2 pi over t, where the uppercase t here is the um, periodicity of your signal. So in this case, 2 pi over t is equal to 1. Okay. Supposedly, the general form of your sine function is a sine of omega t. Okay. And omega is essentially 2 pi over t, the uppercase t. Okay. Which again, the uppercase t here is the periodicity of your signal. Okay. So here, it turns out that in our particular case, it turns out that 5 sine of t, this 2 pi of t is actually equal to 1. Okay. That is actually equal to 1. Okay. Now, solving this for the periodicity, we find that your signal is periodic for 1 over 2 pi. Or I mean 2 pi. Okay, mali pala yung signal. Okay, sorry. This is t equal to pi. And then assuming that that your system, or that your signal carries is defined in seconds. Okay. Or the time element in your signal is in terms of seconds. Then the periodicity of your sine function, 5 sine of t, is actually 2 pi seconds. So it means that 5 sine of t would repeat every 2 pi seconds, or around 6 point something seconds. Okay? So ganito, para medyo saktuhan yung natin, yung periodicity natin. Okay. Let's put in some value there. Let's try to put in say instead of 5 sine of t, let's put in 5 sine of 2 pi t. Okay? Which would now make, okay, this, okay, 2 pi over t. This is scaling factor, which is omega, okay, or 2 pi over uppercase t, okay, equal to 2 pi. Okay, and that would make now your periodicity equal to 1 second. Again, assuming that this time here is actually in seconds. So it means that every 1 second your signal would repeat. Okay, would be repeating. Okay. So let's adjust it furthermore. Okay. Let's adjust it furthermore so that the period becomes, say for example, 3 seconds. Okay. So if period is 3 seconds, then this should be expressed as or omega, okay? Omega should be expressed as 2 pi over 3. So our signal, 5 sine of 2 pi t over 3 would be periodic every 3 seconds. Okay? Let us verify that one. Okay? Let us verify that one by actually plotting these signals. So let's erase those signals. Okay? And then we have f of t. Okay? Our original f of t. So let's call it f1, f0 of t. Okay? Equals 5 times sine of 2 pi t over 3. Okay. So as you can see, as we inspect, by the way, I forgot to mention the 5 parameter. Okay. 5 here is the amplitude. It means it tells us how high our the variation is from the from x equal from y equals 0. Okay. So in this case, that variation is measured from here to here. How much does it vary? Okay. So as you can see, this is 0 and then this is 5. So therefore, it varies from 0 to 5. And that is the amplitude of your signal. Okay. But what we are concerned more of is the periodicity. Okay. So as you can see, your signal from here to here, okay, and then here, and then up to here, it actually repeats after that. The values after that is actually repeated. So ito nga yung pinag-usapan natin before na periodicity. This is the periodicity we are talking about. But as you can see, okay, how long it would take this for the sinusoid to repeat itself? That's 3 seconds. Okay. So ayun, after 3 seconds, uulit na naman siya. Okay. And that is how we designed our signal. Okay. So that's your original signal. Now, how does the unit step function play a role? Okay. Let's say, for example, let's define a unit step function, say u of 0. Okay. U of 0 is a unit step function that doesn't have a delay. So it means it's simply defined as for positive t, yeah, it is 1. Okay. While for negative t, it is 0. Okay. So that's how your unit step function looks like. Okay. Now, let's observe what would happen if I actually multiply those two functions. Okay. Pero as you can see here, dito pa lang, you would be able to see that if you actually multiply those two functions, the values of your f of t, the original function, okay, would actually become 0 when you multiply it with the unit step function. So all the values from here and up to the negative infinity becomes 0. So therefore now your signal becomes a right-sided signal. Okay? It means that all the non-zero values are on the right side or when t is positive. Okay? Let me take a screenshot of this one so that I can place it on your class notebook. Let's place it here. So, let's move your cursor muna pala dito bago natin i-multiply. I-paste. Okay, there. Now, wait, I think I lost the... There. Okay. So again, as I was mentioning, if you actually multiply this black line, okay, or the values of this black line to this violet sinusoid, okay, at this area when t is negative, okay, the product would become 0. Okay, so you'd see that this purple sinusoid on the left side of t equals 0, this is your t equals 0 line, this one, this thick line here. Okay, so to the left of that, your signal vanishes. It becomes 0. Okay, and then here, if you actually multiply this on the right side, when t is positive, okay, your signal is essentially the same. Yung, kasi take note, this is 1. Okay, so if all the values of this purpose signal is multiplied to 1, then it would retain its value. Okay, say for example, kung ang value nito ay sabihin natin 3.3, you multiply it by 1, it's still 3.3. Okay, or something like this one. Say for example, this is negative 0.9. Okay, if you multiply this negative 0.9 by 1, that's still negative 0.9. So therefore, what would happen is that here your signal vanishes. In the left side, your signal vanishes, while on the right side, your signal is retained. Okay, so we can see that if we actually do that, do that operation. So let's call it F1. Okay, which is basically the product of F0, okay, equals F0 of t, okay, multiplied to u of 0. Okay, and the red line describes it. Okay, so if you actually turn off the other two signals, you would have that as the product f of 0 times u of 0. Okay, and this would actually be more interesting if we actually delay. If we actually introduce a delay here. Okay. Say for example, let's produce a step signal that is delayed by 3 or by say 2 seconds. Let's delay your signal by 2 seconds. Okay, so let's have u2. Okay, so u2 of t, okay, equals so if it is delayed by 2 seconds, it means that when t is greater than 2, okay, that is when your signal is 1. Okay, while it is for t less than 2, your signal is basically 0. So that's u2. Okay. Now, if you actually multiply the base signal, okay, if you actually multiply this base signal, okay, with that one, okay, what would essentially be happening is that your signal would be simply multiplied by a step function, and it would retain values when your step function is 1. While those values of f of t, okay, that overlaps with u of t equals 0 part, okay, that is when your time is less than 0, then that becomes 0. Those values become 0, okay, which we can see here. So we can have this as f of 2, okay, of t, okay, to be equal to is equal to f of 0 of t multiplied to u2 of t. Okay, so that is traced by the green line. Okay, so here you can see the contrast between so my signal starts at t seconds, okay, at t equals 2 seconds. So ayan, my signal starts there. Okay, my signal starts at this point, and this is basically multiplying multiplying your base signal 5 sine of 2 pi t over 3, okay, multiplied to ut minus 2 in our notation. Okay, in our notation, this signal, let's have a screenshot of this one. Okay, so let's bring your graph here. Okay, so here we are attempting to graph what we call the delayed sinusoid. Okay, but it's essentially not delayed. Okay, basically because again, as you can see here, if I actually superimpose this to the original, okay, as you can see, although your signal, your f of 2 starts late, it actually picks off from where the original signal gets from. Okay, so pagkatapos nung kumbaga parang dito siya nagsisimula siya doon sa value na to. Okay, which is the value that the value where your original sinusoid ended. Okay, just for it gets multiplied with u of t. Okay, so ganito siya. Yan. Okay. But you might want to say, for example, instead of making this the delay, okay, or making this kind of delay, you would want to instead start your signal, okay, from 2 seconds. So instead, you would want to say, for example, this to start here actually. Okay, so that essentially your signal, your f of t is delayed by 2 seconds. The entire thing, your f of t is delayed by 2 seconds. Okay, and we can do that by multiplying um, f0 of t. Okay. Uh, so we start with let's have f3, no? Okay, of t. Okay, which is let's try if Desmos would accept my functional notation. So apparently hindi. Okay, so kasi what would I do is I would subtract a certain number here. Okay, I would subtract a certain number here, which would allow me now to specify. Okay, would allow me to specify how much day would I want my signal to be. Okay, and basically that starts off by having first taking note that to delay the signal, you need to subtract the time variable directly. Okay, so if this is 2 pi, okay, if this is 2 pi over 3 multiplied to t, and I would want to delay the signal by, say, for example, 2 seconds, I would want it to do it this way. Okay. But what essentially I would be trying to add there is that I would like to make it as 2 pi over 3 minus 4 pi over 3. Okay. As the argument for your sign. Now let's see if that would work. Okay. So basically we start with we start with this one. Okay. So I'll just simply copy this here. Okay. And then I'll have to paste it here. Then I'll subtract how much? 4 pi. I'll subtract 4 pi over 3. Okay. So I'll turn this one off first. Now, essentially, you cannot see any difference between this. There's a difference pala because that I turn it off on. I turn the original signal on, and as you can see, that um, it's unfortunate that they have the same color. Okay, so let me try to change the color to orange. Yeah. Okay, so that's weird. This delayed signal, okay, as you can see, has a 0 value at 2 seconds. Okay, it actually has a 0 value at 2 seconds. Okay, so essentially, this is what we consider now a signal that is delayed by 2 seconds because instead of starting 0 at 0, okay, it actually started with another value at 0. Okay, this one. Okay, and if in the original signal, this would not be encountered. Okay, this value would not be encountered until 2 seconds after. That is after 2 seconds. So here, something like here. Okay. So ito. So that should not have been the value of the signal after 2 seconds. Okay. So that instead of your if you can actually observe furthermore that your signal actually starts 0 at t equals 2 seconds. Okay. So yun yung gusto natin. That is our signal to be delayed by 2 seconds. But I would like to erase. Okay. I would like to make the signal really start at and that the values before t equals 0. Okay. The values before t equals 0 be vanished from this plot. Okay. So with that being said, I would like to simply multiply this by u of t minus 2, which is essentially this one. Okay. If I actually turn this one on, as you can see, my signal is 0 from at this half of the or at this point from negative infinity up to positive 2, my signal is 0. So that if I actually multiply f of 3 with u of 2 here, okay, this the values of f of 3 here would actually vanish and become 0. Okay, and what is left of is this one. So we can observe that by multiplying this with u2, okay, of t, okay, which is that one. So essentially now, at t equals 0, okay, let's copy this as a screenshot, okay, and then paste it here. Okay, so let's paste it here. Okay. So as you can observe here, okay, this is essentially what we now consider as this orange, this orange waveform is essentially what what we consider now as f of t minus 2 times u of t minus 2. Okay. So yun na yung natin sa kanya. We consider this now as f of t minus 2 u of t minus 2. Okay? So that's how we interpret yung this graph. Okay. Now, what if I would like to switch my signal on, okay, at 2 seconds. And then I would like to have it turned off after, say, for example, 4 seconds. So essentially, ang gagawin natin is that my signal will just have a value between 2 and 4. And everything else, your signal should be 0. Okay, so non-zero lang siya in between the signal. Okay. We can do that by actually producing a function which we can consider as a window function. Okay. So a window function essentially samples your signal, or takes in your signal, okay, within a certain interval. Okay. It's like parang meron kang malaking vision. Okay. So if you have if you can see, okay, you have a wide vision. But if you actually want to focus on something, okay, just like what they do with horses when they use it to carry people, or something like that, or kalesa, something like that. Okay. You actually would want to place your hands your eyes between two hands so that you can focus on a certain field of vision only. Okay, so in the same manner, we can actually make our signal be more focused on a certain time interval by using a window function. Okay, and there are many types of window function, but essentially what we are trying to discuss here is a rectangular, okay, window function, or a window function that is in form of what we call a rectangular pulse. Okay, and if we want a rectangular pulse as our window function, okay, essentially this rectangular pulse is a difference of two unit step functions that is delayed in different times. Okay, if you actually have two functions or two step functions that are delayed on different times, and then you actually subtract them, okay, what is left is a window, or is a certain interval in which the values are non-zero, or is 1. Okay, and then the rest, and then outside of that interval, the function is 0, or the value of the function is 0. Okay, let's say for example we want this. Okay, we want to have a window function that is non-zero between 2 and 4 seconds. Okay, so essentially what we can do is we can have a step signal that is delayed by 2 seconds, so that's u of t minus 2. Okay, and then another signal that is delayed by 4 seconds, that is u of t minus 4. Now if you actually subtract this, here's the effect when you actually subtract this. Let's define here another signal. Okay, so this is u of t minus 2. Okay, let's define here another signal that is called u of 4. Okay, for the subscript 4 depicts the delay. Okay, so u of 4t equals, this is equal for t greater than 4. Okay, the value of the signal is 1, while for t less than 4, okay, the value of the signal is 0. Okay. So, as you can see here, okay, since medyo contrasting ngayon siya. Okay. As you can see here, the black line is the u of t minus 4. The blue line is the u of t minus 0. Okay. When you subtract these two, okay, when you subtract the two, basically, those lines that overlap, okay, those lines that overlap become 0. And I'm talking about the region from here to here because both of them are 0 in that interval. And then the interval from here and beyond, okay, because both of them are 1 on that interval. So if you actually subtract u of 2, u of t minus 2 and u of t minus 4, what essentially is left out is this. Kasi ito yung 1 minus 0. So 1 minus 0 is essentially 1. Okay? So as you can see, from negative infinity up to this point, the value of your composite function or the difference of those two is 0. From 4 and beyond, okay, the value is 0. And then in between 2 and 4, your signal is non-zero. So we can actually do that by having, say, for example, w for window function of t, okay, equals u2, okay, minus u4. And again, u2 means u of t minus 2 and u4 is u of t minus 4. So if we actually take or if you actually turn off the other two graphs and come up with the graph of the difference, we have this one. So this is the window function that I'm looking for. It's a rectangular pulse. Okay, so let's take a screenshot of this. Okay, so having it here, okay, you now have a window function. Essentially, a rectangular window function. Okay, so this is formed, this window function, okay, let's call it wt, is formed by subtracting u of t minus 2 minus u of t minus 4. And it's essentially, okay, this function now, or this difference now, is essentially 1, okay, between, when your t is between 2 and 4, and is 0 otherwise. Okay, meaning out of that, out of this interval, your function is 0. Okay, so you now have here a rectangular pulse. Now imagine that if you actually multiply this on a, say for example, sinusoid function. Let's say for example, in this case, if you actually multiply that with this one. Okay, if you actually multiply this this window function with your f of 3. Okay, and doing that, say let's have now f4. Okay, f of 4 t, okay, which is f of 3 t, okay, multiplied to w t. Okay, so we have that this should have been t, not 3. Okay, so the blue graph that you are seeing now is the product, and trying to now eliminate other waveforms. You now see that the function now is a width-load version. Okay, so it's only non-zero for that particular interval only. Okay, so with the unit step function, various operations such as subtracting them, which forms a window, and multiplying them with other functions essentially forms a different forms of your function. Okay, especially it actually can allow you to define piecewise functions differently. Okay, when you say a function is piecewise, it means that that function contains some discontinuities at a certain interval. It jumps from one value to another value, and your function may be defined differently at a certain interval. Okay, say for example, for t equals 0 up to t equals 1, your function is defined as a linear function. And then from t equals 1 up to t equals 2, your function is defined as a parabolic function. Okay, and then at some point, there's a jump in between. Okay, so those are that we consider piecewise function. And um having a knowledge of the unit step function, okay, allows you to create those signals. It allows you to recreate those signals, okay, and write those signals or write those functions in in a more in a compact way. Okay. We will take a look into that in one of the examples. Okay. But I hope that this sticks with you. This idea sticks with you. Okay. So let's put this again in a screenshot so that you can refer to this back. So let's have okay. My audio suddenly lost. So as I was saying, this is the windowed function, okay, which is essentially 5 times sine of 2 pi t over 3 minus 4 pi over 3, okay, times u of t minus 2, which essentially delays it by 2 seconds, okay, and then allows it to start at 2 seconds. What delays the signal is this factor, okay. What causes it to start at 0 at 2 seconds is this delay that we have introduced on the function itself. Okay, but here it allows us to read the signal starting at this point, okay, and ignore the signal, or essentially make the value of the signal 0, or make the signal vanish for t less than 2 seconds. Ito yun. Okay, and minus u of t minus 4, which essentially makes your signal vanish for t greater than 4. So from here up to this point, your signal vanishes because of this. Okay. Here, your signal vanishes or becomes 0 because of this. Okay. And your signal starts at 2 seconds. Okay, because of this factor. Okay. So I hope you get the gist of this. Okay. You get a good grasp of and good understanding of how can you use to how can you use your step function, okay, to reshape, okay, your signal. Okay, so there. Now we proceed now with trying to with going on the main issue here, okay, which is about how do we use now Laplace transform in the presence of um, unit step signal. Okay. Now, as you might be able to see that unit step signal can cause your signal to be delayed. Okay. In terms of time. Okay. It can be delayed in terms of time. Okay. And that is where the second shifting theorem, okay, or time shifting theorem of Laplace transform applies in. Okay. Just a recall. Okay. Your first shifting theorem, your first shifting theorem, theorem, stated that if you're taking the Laplace transform of the product of e raised to at times f of t, okay, that is when you have a function multiplied by an exponential. Let's specifically call this as a time exponential or a t exponential. It means it's an exponential whose exponent is dependent on time, or is a time domain. Is an exponential in time domain. Okay, so if you have an f of t, a time domain function multiplied by a time exponential, its Laplace transform is f of s minus a. Okay? Now, this fact or this as you can see, the independent variable of your f, function f in S domain, okay, here is actually subtracted by a factor, a parameter a. Okay, it means that we are actually delaying. Okay, but the delay is not the delay is not a proper term, but shifting. Okay, delay pertains to time. Okay, when you delay something, it means that it is late, and when it's late, it actually connotes a concept of time. Okay, so using delay to describe this operation is not accurate because S is not basically time. Okay, a more appropriate term for this one is actually shift. Okay, so basically your S here, or your function in the S domain is being shifted. Okay, but the shift happened in the S domain. That is why we call the first shifting theorem as S shifting, because the shift happens in, okay, the shifting, okay, happened in the S domain. And what conditions do we use this? Okay, or when will a shifting happen? When in time domain, you multiply your time domain function with a time exponential. Okay. Now, as we now move on to the second shifting theorem, okay, it would be stated in the following manner. Okay, it would be stated in the following manner: shifting theorem. Okay, if you're actually taking the Laplace transform of f of t minus a multiplied to u of t minus a, okay, u of t minus a, that essentially is equal to e raised to negative as times f of s. Again, f of s is the Laplace transform of the function f of t. Okay, so we take note that the Laplace transform of f of t, okay, is basically f of s. Okay, so here you can clearly see here that if this is the case, then if we have ft, then f of ft of a means a shifted version of f of t. Okay, so f of t, okay, f of t minus a, okay, is a shifted version. Okay, f of t minus a is a shifted version of f of t. Okay, and what happens when there is and when or where at what domain did the shifting happen? The shifting happened in the t domain or in the time domain. That's why this is called t shifting. Okay, this theorem is essentially referred to also as t shifting because the shifting happened in t domain. Okay, and what happened and what follows after that? If you have actually a function that is shifted in t domain and is multiplied by a unit step function, and that is a requirement, it's not necessary it is not enough that you just delay the function. You also have to multiply the function with a step function, with a delayed step function. And notice that this is the same a. Okay, it means that you have to delay the function, okay, and the step function in the same amount of delay or in the same amount of shift. Okay, so that is one thing that you have to notice about that. But again, going back to my point, what happens when you shift, okay, or what happens when you delay your signal in time domain or in t domain? Your Laplace transform in S domain, okay, your Laplace transform gets to be multiplied by an exponential. This time, let's call it an S domain exponential. By the way, time domain exponential and S domain exponential are not standard terms used in books. I just invented them, okay? Para lang magkaintindihan tayo when we say time domain exponential and S domain exponential. Okay, so So you can see the duality of the first and the second shifting theorem. Okay, that is, if the shifting happens in S domain, the time domain signal gets to be multiplied by a time domain exponential. While if the shifting happens in T domain, the function in S domain gets to be multiplied by an S domain exponential. Okay? So dual, in this case dual yung okay, dual yung effect niya. Okay, yung first at saka yung second shifting theorem. Okay, and in fact, that duality is also observed. That duality of Laplace transform properties is also observed in the previously discussed property, the Laplace of derivatives and Laplace of integrals. Okay, yung duality na yun is also is observed in that in those properties. Okay. So basically this second shifting theorem is specified in this equation. Okay. But we have an alternative we have an alternative we have an alternative formulation for this second shifting theorem. Okay. So instead of that, okay, an alternative, okay, is that we take the Laplace transform of f of t times u of t minus a. Okay. Which is its Laplace is equal now to e raised to negative as times the Laplace of f of t plus a. Okay. So that's an alternative formulation of the second shifting theorem. Okay. In the next example, I would explain how. Okay, I would explain how how to use this one, the first formulation that we had, and how this would actually make some of the operations easier. Okay, some of the manipulations and application of the second shifting theorem easier than the first form. Okay, so let's take a look at this example. Okay, so first we would like to write this function in terms of unit step function. Okay, and I would leave it as an exercise to you. Okay, I would leave it as an exercise to you. But this is written in function form in this manner. Okay, remember remember this this one. Okay, you can you should be able to remember this because we just discussed this earlier. Okay, remember that for me to be able to produce, okay, this windowed function, okay, that is defined, okay, this 5 sine of 2 pi t over 3 minus 4 pi t, okay, to be defined between 2 and 4. Okay, I did this. Okay, I did this. So trying to extrapolate on that knowledge, okay, you should be able to verify that this function, okay, is written in this manner when you use step functions. Okay, so or you may want to try to graph this function using Desmos. Okay, tulad ng demonstrate ko kanina. Okay, so that you can be able to verify that these two, okay, are the same functions. Okay, basically, pag ito ang i-graph nyo, itong piecewise function na to ang i-graph niyo. Okay, sa Desmos, the first interval can be assigned, say for example f1 of t, okay, which is equal to for t between 0, okay, and 1, okay, you use colon 2. Okay, so that graphs now f1 of t as 2 between t equals 0 and 1. Okay, that graphs this first interval. And you can continue on. Tapos what you want to do is to add them. So produce the signal f of t. Say for example, this is assigned to f2. Okay. This second interval is assigned to f2. Okay. And the third interval is assigned to f3. Okay, the third interval is assigned to f3. Now, in order to combine them, okay, in order to combine them in a single graph, okay, in order that they appear as a single graph, you need to add them. So you need to produce f of t, okay, equals f1 of t, okay, plus f2 of t, okay, plus f3 of t. So that's one way that you can graph this function. Okay. Okay. Now, as an alternative, you can directly, okay, try to use unit step functions in order for you to graph this function. Okay. And again, as I demonstrated earlier, okay, I have shown you how to define this, okay, and how to use them in Desmos. Okay. So, yun, you will be able to verify you will be able to verify those stuff, okay, using Desmos. Okay. Now, what I like to do now is to try to find the Laplace transform of this one. Okay. And in that case, I would like first to concentrate on the second term. Okay? Because this is where the first form of the formulation for the step function or for the Laplace of the step function gets really complicated. Okay? So I'll take that one out. Okay? So let's have it as 1/2. Okay, 1/2 t square times 1/2 t square times u of t times u of t minus 1. Okay. U of t minus 1 minus u of t minus 1/2 pi. Okay. So that's the second term. Okay. So for us to be able to get the Laplace transform of this, we need to expand this one. Okay. We need to expand this as 1/2 t square u of t minus 1, okay, minus u of t minus 1/2 pi. Okay. Sorry, kulang pala ako. I forgot to kasi nga di-distribute eh. So okay. This factor gets to be multiplied here and then here. Okay. So you still have 1/2 t square u of t minus 1/2 pi. But I would like you to be very careful with this one because you might be looking at the equation where you might get functions mixed with variables. Okay, as a reminder, u is a function. Okay? And what comes after u is a depiction of its independent variable. And what happens to your independent variable? Okay? So therefore, you don't multiply u with t here. Okay? Because basically, this is an independent variable. Kumbaga, we take this as a single symbol. We take this as one and cohesive symbol, not separate entities. So they don't get multiplied. Okay, that's my point. Okay, so be very careful when you look at this at this kind of expressions. Also, may I just interject with this topic? Talking about notations. Okay. At one point of this problem, this particular example, you have to write something like the cosine of yung last term. Cosine of t. Cosine of t times u of t minus 1/2 pi. Okay. Now, what you can see at the example itself. So what can you see with the example itself is that the example have written this in this manner. Okay, and that's okay. Okay. My concern kasi is this one. If you actually be very careless with this one, you might actually be accidentally writing this as cosine of t u of t minus 1/2 pi. And if you don't have a good sense of your writing, okay, you might interpret this as being multiplied. This t is being multiplied by this u. Never mind that you may confuse this u to be multiplied here. And so everything gets mixed around. Okay, so that's a problem there. Okay. So you are now on the point of studying math that really involves complicated equations and complicated expressions. Okay. So you might want to make some or to develop some habits when writing these equations. Say for example, like this one. Okay. One of the safest way to do this is to introduce parentheses. And that makes it not ambiguous. Okay. That makes it clear. Okay, that you have to multiply this with this one. Okay. That's good. Okay. And conventionally you have to multiply this this way. You have to multiply it this way. But what I would like you to see, what I would like you to improve on is something like writing expression something like cosine of t multiplied to e raised to negative t. Okay. When you're trying to write an expression that involves a sinusoid function and another factor, okay, I would like to recommend that you put this, that you write this in a manner that the other factors or factors other than the sinusoidal function, okay, to be on the left of that sinusoidal function. Okay. Or some not necessarily sinusoidal function, but also to logarithms. Like for example, instead of writing ln of x times 1 over x, which if someone would actually read this and was not able to get the context of what you are trying to do, may interpret this as this way. Okay. Instead of actually writing it this way, you may want to consider writing it as 1 over x times ln of x, which is which is clearer, which provides more clarity than this one. Okay. So you may want to since you are dealing now with a lot of expressions, okay, you may want to consider developing this habit of making your expressions or making your handwritten expressions much more clearer. Okay. Especially on my side, okay, because if I am not able to interpret your writings correctly, I might score your papers incorrectly also. Okay. And that would put in some delays, considerable delays in assessing your papers. Okay. So, yun, the reminders lang. Okay, going back here. I write here the formulation, okay, the first formulation of the second shifting theorem. That refers to equation 4. Okay. So equation 4 says that the Laplace of f of t minus a multiplied to u of t minus a multiplied to u of t minus a, okay, equals e raised to negative as, okay, times f of s. Now, what you need to understand about this formulation is this. You would need to recognize that you need to be consistent with this form before you can actually apply it. Okay? So, ano yung kailangan yung tingnan? You see that both f and u, okay, both the functions f and u, contain the same amount of shift. Okay? So, if you are considering to use this form when taking the Laplace transform of a function, you might want to consider that these two should have the same, or this function should have the same amount of shift. Okay? So, for example, in this case, if you consider this, okay, as your f of t, if you consider 1/2 of t squared as your f of t, okay, and u of t minus 1 as your unit step function, okay, so this is u of t minus a. You should recognize that you might want to recognize the fact that they don't possess the same amount of shift. So therefore, you have to change this f of t so that it would contain the same amount of shape as this one. So in that case, you would so since the delay for your the delay for your the delay for your unit step function is 1, okay, then you would want to change this to f of t minus 1. Okay, that means if this is 1 half t square, okay, f of t minus 1 is actually equal to backward. I wrote equal to downwards. Okay, I'll just use an arrow. F of t minus 1 is equal to 1 half of t minus 1 squared. Okay. So remember that this function notation allows us to specify what would we want to do with the independent variable. Say for example, if you have f of x equals 2x plus 1, and if you say that you would like to evaluate f of 2a plus b, okay, then that should be equal to 2 times 2a plus b plus 1. As in, whatever is this, whatever the independent variable becomes in a function notation, you would replace that independent variable with whatever that is here. Okay? So which means, kung f of t minus 1 ito, we will have to change this t here with t minus 1. So that becomes this one. So we multiply it again with u of t minus 1. Okay? But again, notice that the change now that you are consistent with the definition of the formulation of the second shifting theorem, okay, you might want to take a look back that this expression is not equal to this. They are not equal because you added another number. So therefore, this is not equal to this one. So let's try to make them equal. And to do that, we need to recognize that we need to recognize what terms or how much terms we have added. Okay. So to do that, let's expand this. Okay, let's expand this expression. So we will have 1 half of t square u of t minus 1. Or say, unahin lang muna dito, itong part lang na to. Okay, so that's t square minus 2t plus 1 times u of t minus 1. Okay? So, here, if we actually expand this completely, we will have 1 half of t square u of t minus 1. Okay? Minus, this is 2t times 1 half. So, that becomes t. Okay? T times u of t minus 1. Okay. And then this is plus 1 half of t. Oh, sorry. 1 half of simply u of t minus 1. Okay. So we have this. We have this as the expanded version of the new form. And as you can see, this is your original term. This is the original term that you had. But when you change it in compliance with the form suggested or required by equation 4, okay, you have essentially added this term. So you have added this term. Now, for you to be able to maintain the value or maintain the value essentially of your expression, okay, maintain the value of this expression, you need to eliminate these terms by, this is now your change now, okay, by actually negating the effect of this to this. Okay, so which means that I have to add the term t times u of t minus 1, okay, u minus 1 here, okay, and then subtract this minus 1 half u of t minus 1. Okay? Now, that essentially, the effect of this one, adding this term, is essentially adding these terms here. So, you simply add t, u of t minus 1 here. Okay, plus or minus, okay, minus 1 half u of t minus 1 there. Okay. And evaluating this entire expression would lead you back to the original term, which is this one. Okay. So there, we ensure now that, so now we are sure that this and this are now equal. This expression, okay, including that these terms, okay, and this expression, they are now equal. Okay. So there. And then that's the time that you can apply now the formulation form. Okay. But as you can notice here, your expansion actually gave rise to another term that is not in compliance with the formulation set by equation 4. So you have to do this process over again. So that you change that to you change that to um let's use another color. Let's say red. Okay. We will change this to t minus 1 u of t minus 1. But again, this is not the original, or this is not essentially this does not essentially possess the same value as that of the previous expression. And essentially, you have added this term because if you expand this, okay, if you expand this term, okay, the one written in red, okay, this becomes t u of t minus 1, tu of t minus 1, minus u of t minus 1. Okay? So that you return back to the original expression, you need to add this term. Okay, you need to add this term. And then of course this this allows us to change this this term into this. So let's try to do that. Let's erase this one and write that as t minus 1 multiplied to u of t minus 1. Okay? But to maintain equality between these expressions, okay, I need to add this term, this u of t minus 1 here. Okay? So that as you can see now, all of the terms here comply with equation 4, the formulation set by equation 4. Okay. And then let's simplify this, the writing of this. Okay. Let's simplify the how is this written. Okay. So let's have it as 1 half times t minus 1 squared u of t minus 1. Okay. Plus t minus 1 times u of t minus 1. And if you can notice, the last two terms, this term and this term, okay, are simply constants multiplied to the step function, okay, having the same amount of delay. So they can be reduced into a single term. Okay, so that simply is adding negative 1 half with positive 1. So that's positive 1 half. So we can have this as plus 1 half u of t minus 1. Okay. So these three terms now are in these two terms at least are consistent with the formulation set by equation 4. Okay. So that is now the time that we apply now, okay, or that we now obtain their Laplace transform. Okay, again, that is the Laplace of f of t minus 4, t minus u of t minus a, okay, is e raised to negative as times f of s. Okay? So, again, applying the formulation set by equation 4. Okay, this is equation 4 now. Brings us that to find fs, we need to identify f of t. Okay? So, in this case, here, f of t is essentially t squared. Okay? F of t is the is the unshifted version. Okay? You remove all the shifts, and that's f of t. And then here, we see that f of s, given that this is f of t, okay, we see that f of s here is now 2 over s cubed as per table 6.1. Okay? But applying this formulation, that brings us to the fact that we need to multiply this f of s with e raised to negative as. Okay? And then multiply that with this constant. So, the transform of this term, just this term, is 1/2 multiplied to f of s, which is 2 over s cubed, and then multiplied with, multiplied to e raised to negative, a here is 1. So, this becomes 1, so that becomes e raised to negative s. Okay, and simplifying this term, or kamaya na lang, we proceed with the second term, okay, here. Okay, and again, here, your f of t is, again, we remove all the delays. That's a simple t. So, it's the Laplace transform, okay, is essentially 1 over s squared. Okay, again, as per table 6.1. Okay, so therefore, the constant, which is 1, okay, multiplied to this as your f of s, so that's 1 over s squared, and then let's multiply it with the s domain exponential, okay, which is e raised to negative s. Okay, now I hope that you are getting the the handle of this, okay, because I would not solve all of the terms, okay. I would let you solve the other terms there, okay. And then finally this one, okay, we will use actually this can be applied also, considering that you can have f of t equals 1, okay, which it's the Laplace transform as per table 6.1 is 1 over s. Okay, and therefore you now have the constant 1/2 here multiplied by the f of s 1 over s, and then multiplied by the s domain exponential, which is e raised to negative s. So simplifying everything, at least for this term, okay, for this particular term for this particular term that we have here, okay, this particular term that we have here, okay, is essentially, so na yan. Wala. Okay, that is essentially ayun, 1 over s cubed, okay, plus 1 over s squared, okay, plus 1 over 2s. And then I'll multiply everything with e raised to negative s, because e raised to negative s is common in 3 terms. Okay? So, ayun. You can actually see this this set of terms. Okay, here. Ito siya. Yan. So, there is the this terms of the Laplace transform actually correspond to this term only. Okay, and you may be able to get other terms. Okay, for example, these terms come from this term. Okay, this set of terms come from here. Actually, you will be able to see that using this this s domain exponential. Okay, because the exponent of that s domain exponential actually tells us how much delay you have in your or how much shift your step function has. Okay, for example, itong negative pi s over 2 actually corresponds to a delay or a shift in your step function as 1/2 pi. So I hope you are able to recognize that or you are able to observe that that form. Okay, so now at this point, I would like you to work on the rest of the terms. Okay. having been demonstrated with one of the terms. So, everything else would follow naman. Okay? So, ayun. But again, if you're having problems, you can ask questions. Now, I would like to provide an alternative in which, again, the difficult part of using the original formulation is the fact that you have to probably do some additional operations just to comply with the form set by equation 4. Okay? But those operations can actually be minimized, okay, by using the alternative, which is this one. Okay? Now, let me show you how does that apply, okay? And with this term, okay? Again, we start with this term, okay? 1/2 t square times u of t minus 1. And I would like to place the solution near dun sa solution natin kanina so that you would be able to compare the two. Okay? And then smile later after I am done with this one and see that uh, you see for yourself later on. Okay? So again, the alternative formulation identify which is I did by 4 and double asterisk. Okay? Let's just say this is the alternative formulation. States that the Laplace transform of f of t. Okay, the Laplace transform of f of t times u of t minus a. Okay, equals e raised to negative as multiplied to the Laplace transform of f of t plus a. F of t plus a. Okay, that is the alternative formulation. Okay, let's apply it here. So number one, according to this alternative formulation, there is no requirement of your function and your step function having the same amount of shift. So if they don't have the same amount of shift, it's okay. Okay. But the thing is that what you would like to observe is that this doesn't have a shift at all. So your f of t is not shifted. So this would be a problem if f of t is shifted in another amount, okay, as that of your step function. So that's another if that case arises, I would refer you back to the original, okay, and try to do the shift, okay, using the same amount of shift with both the function and the step function. Okay, but since here what we're talking about here is that your function doesn't have a shift, okay, and then this is multiplied to a shifted step function. So basically, ito nagko-comply na siya dito. So consistent na siya dito. Now what do? We just simply find first, okay, we just simply have to find first the Laplace of f of t plus a. So again, here f of t plus a means you have f of t, okay, and then you shift t with negative a. Or that essentially makes your f of t move to the left. Okay? That makes your f of t move to the left. Okay, pero mathematically, that means ganito lang. We identify first what is f of t. Okay? We identify what is f of t. Okay? And then, so in this case, this is 1/2 t square. Okay, and then we form f of t plus a. Well, in this case, a here is 1. Okay? So f of t plus 1. Which is 1/2 of t plus 1 squared. Okay. Now, we get the Laplace transform of this. We get the Laplace transform of f of t plus 1. We will get its Laplace transform. Okay. Which, for you to be able to do that, okay. So, let's get the Laplace transform of 1/2 t plus 1 squared. For us to be able to get the Laplace transform of this, we first expand yung function natin. Okay. So let's try to find the Laplace of 1/2 times t squared, diretso ko to t squared, plus this is 2t. Okay, the middle term, this is 2t. Then multiplied by 1/2. So that's t essentially. So this is t. And then this is 1 squared plus 1/2. So this is simply 1/2. Then its Laplace transform, okay, is then t squared is essentially 2s over 3. Okay? T squared is 2, the Laplace transform of t squared is 2s over 3. And then multiply that out. Let's write it down. So 1/2 times 2 over s cubed. What I was saying. 2 over s cubed. The Laplace transform of t squared is 2 over s cubed. Okay? And then plus the Laplace transform of t is 1 over s squared. And then the Laplace transform of 1/2 is simply 1 over 2s. All are based on table 6.1. Okay, and simplifying this one, okay, you have now 1 over s cubed plus 1 over s squared plus 1 over 2s. And then, so that's the Laplace of f of t plus 1. Okay, that's the Laplace of f of t plus 1. Okay, which now is this part. What needs to be done now is to multiply this with this exponential so that you get the Laplace transform of this one. So the Laplace transform of this one is e raised to negative as. A is 1 in this case. So you have e raised to negative s multiplied to this, which is 1 over s cubed plus 1 over s squared plus 1 over 2s. Now at this point, okay, and looking back at what we have done in the previous in a previous solution that used the original formulation of the second shifting theorem, you judge and you observe. Okay, so again, what I would like you to do, okay, di ba naasaya? Okay, so what I would like you to do is to actually complete this solution, okay, by having or by solving for the Laplace transform of each of these terms. Okay, this might be a little, you might be intimidated by this term. Okay, but try using the original and then try using the alternative. Okay, and see that this term is not actually that difficult to evaluate. Okay, so from that at that perspective, you would be able to formulate general although one of the reasons why this is not really that hard or that difficult to evaluate, the Laplace of this is not really difficult to evaluate, is because of the delay. Okay, you'll figure it out when you actually do this one. Okay, and that consider the fact that cosine of pi over 2 is 0 and sine of pi over 2 is 1. Okay, so there. So either you use this or this. Okay, and essentially that would lead you to the same answer. Okay, so I would like you to try and work on that note. Okay, and see for yourself how this two would actually play out. How the use of either of this or this would actually play out, because at this particular example, this might be a devil. The original formulation might be a devil in your mind, meaning nasiraan ko na to. Okay, you observe that this involves more a much number of operations compared to this one. Pero that is not the case at all times. There are times that this is actually easier to use than this one, than the alternative. Okay, and there are times that the alternative is easier to use than the original original formulation. So you try to figure out yourself when is 4 okay and when is 4 double asterisk okay to use. Okay, create your own rules. Try to create your own rules with this one. Okay, so so that this would actually be a very kumbaga kayo yung nag-develop nung parang thinking kung kailan nyo gagamitin ito at kailan nyo gagamitin ito. There is actually a pattern in that. Okay. There's a pattern in that. And I want you to discover that pattern. Okay? So, there. Now, here, okay, for example 2. Okay. For example 2. We are asked to find the inverse transform of this one. Okay. So which means from f of s, we would like to find what is f of t. Okay. So in this case, this is simply isolating first yung S domain exponentials. Okay. At least in this particular example, pero in general, you can develop that mindset that when you're taking the inverse Laplace transform and you see that there is an S domain exponential there. Okay. You first isolate that. Okay. And come up with the inverse Laplace transform of the remaining factor, which is in this case 1 over s squared plus 5. Okay. And in that case, if you actually evaluate the inverse of this, okay, this should become 1 over pi, okay, 1 over pi times sine of pi t. Okay, that should be 1 over pi times sine of pi over t. Okay. Now let's get back the let's set the S domain exponential back. Okay. So since there is there's an S domain exponential here. Okay. It means that it came from f of t minus a. Okay. Times u of t minus a. Okay. The Laplace of that is e raised to negative is equal to e raised to negative as times f of s. Okay. So since you have isolated this f of s first at the earlier step of this solution, okay, and then you have already taken the necessary step to compute for f of t, okay, which in this case is now in this particular case that in this particular example that we are talking about, this is now 1 over pi, okay, times sine of pi t, okay. Then in compliance with this form, okay, you produce now f of t minus, in this case, a is, we find from e raised to negative as that a is 1. Okay, so in this particular example, we have a equals 1. So therefore, we have to find f of t minus 1. So that means, from here, we simply have to replace t with t minus 1. Okay, so we'll have 1 over pi times sine of pi t times t minus 1. And then, to complete the steps, we need to multiply this f of t minus 1 with a unit step of the same delay, u of t minus 1. So now, this becomes simply 1 over pi times sine of pi t minus 1. T minus 1. Okay? Times u of t minus 1. So for the first term, okay, this is its inverse. That is for this term. Okay. You do that, you can apply those same steps, same procedure with the second and the third term. And then you try to simplify things afterwards. Okay. If there is something to simplify. Pero kapag wala, okay lang naman na iwanan nyo na lang siyang ganun. Like what the example did here. Okay. These two terms can actually be simplified further. Those two terms can actually be simplified further. Pero by expanding the sign part. Okay. But the example did not bother to do that. So okay na yan. Actually, you can use Desmos to graph this function and come up with this kind of graph. So as you can see, your graph is defined differently in different intervals. From here to here, okay. From 0 to 1, it is different. From 1 to 2, it is different. From 2 to 3, it is still different. And from 3 and beyond, that is still different. So iba-iba siya per interval. And that is not a theoretical thing. Okay? That actually arises in the practice. Okay? When you are doing some research about a certain system, okay? That these things, this kind of signals actually are possible in the practice also. Okay? So there you can apply these steps. Okay. These are the steps. You first isolate the you isolate the S domain exponential. So isolate I'm talking about second term na. Isolate e raised to negative 2s first. Okay? And observe that f of s, okay, equals 1 over s squared plus pi squared. That's the first step. Okay? So that's 1. Okay. Number 2, find the inverse of f of s. So let us find the inverse of 1 over s squared plus pi squared, okay, which should give you 1 over pi sine of pi t. Okay, I would like to verify why it became 1 over pi sine of pi t. Okay, pero this is again consistent with this is consistent with table 6.1. Okay, this inverse is consistent with what the table 6.1 requires us. Okay. Okay. So step 3. Okay, step 3. Use yung equation, yung formulation ng Okay, that is you first since you now have f of t, okay, you produce now f of t minus a. So you produce now f of t minus a from f of t. Okay. From f of t. Okay. So that means that you have to identify a from here. So a here is 2. Okay. And therefore, you would have something like f of t minus 2 is essentially 1 over pi times sine of pi times t minus 2. Okay. So, ayun. And then finally, you multiply this with a unit step function having the same delay. So you have f of t minus 2 times u of t minus 2. Okay. Makes this 1 over pi times sine. Para mas malinaw to, let's put in some parentheses here. Okay. So this is sine of pi times t minus 2. Okay. Multiplied to u of t minus 2. Okay. So try to complete this example. Okay. By working on the third term. I've already done the 2 terms. So again, para may practice kayo, work on the third term. Okay. And then here finally we have example 3, which now deals with circuits. Okay, which now deals with what we call a RC circuit. So RC circuit means that your circuit contains a capacitor and a resistor. Okay. So here you have a rectangular pulse, okay, as an input to this. Okay. You have a rectangular pulse as an input to this. Okay. So how do we now try to come up with with a solution here, since we are looking for the current. Okay. If it is current that we are trying to find and we have an RC circuit, then the easiest way, or the law that would actually give you current, okay, in this series RC circuit is the KVL. Okay. So by taking KVL here, okay, you would be having an equation. Okay, you would be able to have an equation. But before I actually take KVL, this would actually be easier to deal with if you take the Laplace transform of everything. Okay, but that also involves using impedances. Okay. You might have not yet heard of what impedance is. Impedance. Okay. Impedance. Okay. But impedance actually refers to the um to the to manner by which your circuit tries to stop changes in voltage or in current. Essentially in current, okay? Kasi nga impedance siya in terms of current. It is much more of a resistance, okay? But resistance kasi only applies to resistors, okay? And furthermore, resistance only applies to the ability of your circuit to resist change in direct current, okay? Or in the amount of direct current. Okay, so parang yung resistance pinipigilan niya yung pag-flow ng current niyo, ng direct current niyo. Okay? But it doesn't do anything with how current is changing. Okay? Impedance is more appropriate to describe that situation. Okay, that is when you try to that is when you try to describe the ability of your circuit to try to resist changes in current. Okay? When your current is trying to change, your circuit would try to delay that change. Okay? Would try to slow it down. That is impedance. Okay? Just to make everything short. Okay? In Laplace transform, okay, or in S domain, we can these circuits, okay, or these components, the capacitor, okay, the capacitor and the resistor. And later on, pag gumamit tayo ng inductor, okay, these have impedances in S domain. Okay? This would have impedances in S domain. And we without proving at this point, let's write them as follows. The impedance of the capacitor, okay? The impedance of the capacitor in S domain, okay, is 1 over CS, where C is the capacitance of your capacitor. Okay? Resistor, the impedance of the resistor in S domain is simply R. Again, walang gagawin sa change in current yung niyo. Okay, yung resistor niyo. It can have an effect on DC, but it doesn't have an effect on alternating current. Okay, or changing current. Okay. So it's simply R. Okay. Inductor, okay, has a we call C as the capacitance. Okay, and in your circuit analysis, your capacitance is defined as the ability of your capacitor to store electrical energy in the form of electrostatic field. Okay, so that's capacitance. Inductor, okay, yung impedance niya in the S domain is written as LS. S is the S domain variable. Okay. So L, okay, is what we call the inductance. Okay. And inductance measures the ability of your inductor, okay, to store energy in a magnetic field. Okay. So ito capacitance stores or measures the ability of your material to store electrical energy in electrostatic field. Okay? While the inductance measures the ability of your material to store electrical energy in magnetic field. Okay? Units, ang unit ng capacitance is in farads. Okay? Ang unit ng magnetic field ay Henrys, H. Okay? Of course, ang unit ng resistance is ohms. Okay, so please do remember that. Okay. Now, when you are analyzing circuits, okay, and especially if that circuit is in or involves alternating current, okay, or involves an input voltage that is something like this, okay, if it involves a voltage something like this, you may want to use Laplace transforms, okay, to analyze a circuit. And aside from aside from taking a good look at how the voltage input is expressed, okay, you might also want to look if there is a capacitor or inductor, okay, because in the presence of those components, your equation, the model that would describe your circuit would actually become a differential equation, or in fact it becomes a integral differential equation, a combination of an integral equation and a differential equation. um, that is, in one equation you have an integral term and you have a differential and you have a derivative term, so you call that an integral differential equation, which you don't want to work on. Although one way to work on that is to actually change, instead of writing the equation in terms of current, you write the equation in terms of charge. Okay? For example, the voltage, okay, ganito kasi yan. It starts with the voltage, okay, that flows through a capacitor. So we call it VC of VCT. Okay. Is equal to 1 over C times the integral of I tau d tau. Okay, from I think this is from 0 to t. Okay. So that's the voltage flowing through a capacitor, okay, given the current. So you have to integrate. Okay. And then yung inductor naman, the voltage across the inductor, okay, is L times the derivative of the current with respect to time. Okay. So if you actually if actually your circuit contains both an inductor and a capacitor and a resistor. By the way, the voltage across the the voltage across a resistance, okay, is essentially R times I. Okay. It's simply R times I. Okay. So, ano yan? Consistent yan with Ohm's law. Okay. Ohm's law. Okay. Now, what we do here is that if you have a circuit, you need to do what we call a KVL for a series circuit. Okay. So halimbawa, meron kayong circuit such as something like you have a voltage source here. So that's V of T. That's your voltage source. And then say for example, you have a resistance, an inductance, and a capacitance. Sorry, a resistor. I'm talking about components pala, no? A resistor, an inductor. Okay. You have a resistor, an inductor, and a capacitor. Yeah. So this is R, L, and C. Now, if there is if this is a circuit, a series circuit, okay, and you would want to get an equation from this one, okay, you would have to do, or you would have to use what we call the Kirchhoff's voltage law, or simply call this KVL. Okay. Okay. So this KVL states that the sum of voltages around a loop is 0. Okay. And so it means for this circuit, if I actually add this voltage and the voltage across this and the voltage across this and the voltage across this, if I add all of them, okay, that should amount to 0. Okay. But when you're doing KVL, you are also considering potential drops. Okay, that is, you always think that the voltage in a series circuit or in a loop, something like this, okay, your voltage would drop after passing by a certain component. Okay, so therefore the voltage drop there is negative. So that is why if you start with V as the source, okay, V of t as the source, or let's simply use V there. Okay. Let's simply use V. Okay. Um, if if your current passes through this resistance, the voltage would drop right there. Okay, there would be a considerable voltage drop. Okay, so that voltage drop actually um lessens the source. So that we will have at this point after your current pass through the resistance or the resistor, you would now have V minus VR as the potential after the resistor. Okay? And then after your current passes through here, again, there's another voltage drop after your current passes after the inductor. Okay? So that's another voltage drop there. So that makes it minus VL. And then at this point, if your current passes through the capacitor, there's another voltage drop there. So that diminishes another voltage. So that becomes VC. And and since those are the voltages, okay, around this loop, okay, these are the voltages around this loop, okay, the total of which should be 0, okay, and that's KVL, okay. Okay. So that's KVL. Now, you can actually proceed by substituting this, okay, here, okay, and imagine, okay, you can substitute this this three voltage, we call this voltage current relationship because you relate voltage with current, okay, in all of these cases. Okay, so you can substitute this voltage current relationships here, and just imagine that if you have an integral, okay, and a differential appearing in a single equation, then that's what that is what I call the integro differential, okay, equation. Okay, which can be solved. Okay, it is possible that we can solve this kind of integral differential equation. Okay, it is just that there are easier ways to work on this. Okay, there are easier ways to work on this rather than forcing yourself to deal with an integral differential equation. Okay, so you can look at that as V minus VR is R times I. Okay, and then VL is L times DI over dt. And then VC is 1 over C times the integral of I tau I tau d tau, okay, equals 0. So again, this is something that I call the integral differential equation. Okay. Now, an easier way to work around this integral differential equation is that instead of expressing this in terms of current, you can actually express this in terms of charge. Okay. In terms of charge, again, you would have to replace I with the derivative of your charge. Again, the two quantities are related. Charge and the current are related in such a manner that the first derivative of the charge, okay, or the time rate of the charge is equal to the current. So if you actually replace I with current here, okay, I with current there, and then I would try to transpose all of the negative terms on the other side, okay, so that everything is positive, and that I would just place the voltage source on the right side, okay, and then the one with the variables on the left side, okay, and at the same time replacing I with dq over dt, or the first derivative of q with respect to t. I'll have the following. This is r dq over dt, okay, plus L, the derivative of I, okay, when I replace I here with dq over dt, means I'm taking the second derivative of q, with respect to t. Okay? Kasi yung I, dinerivative ko. So pag kung ang ipapalit ko dito is another derivative, okay, that means I'm taking the second derivative of that quantity. So I'll have this one. Okay? And then finally this is 1 over since I'm replacing this with dq over dt, and then I'm integrating that. Okay? That means this is simply q. Okay? This is simply 1 over c. 1 over c times q. And that is equal to v. Okay? So rearranging this so that this becomes a proper differential equation. This is L dq square over dt square plus r dq over dt plus 1 over cq equals v. Okay. This is one way of solving this kind of problem. If it appears that you have a differential and an integral in the same problem. Okay. But just remember that you would be, if you solve this equation, okay, you would be solving for q of t. And so to be able to find I, you need to find the derivative of this with respect to time, so that becomes I. Okay. So I'll try to continue the discussion this on another video. Okay, since this is kind of 2 hours na pala. Okay, so I'll continue the discussion on another on part 2 of this video. Okay. So sige.